Well, hello everyone, and welcome back to Adrian's Digital Basement. On today's video, we're going to be going back to the Southwest 6800 computer here. On the last videos, multiple of them, when I looked at this machine, I got it working, I upgraded the RAM to the max 48K that this particular one can support, but what we didn't look at was the floppy drive interface, and I have it right here in my hand. This is what came with this computer. It is the Smoke Signal Broadcasting BFD-68, BFD standing for Basic Floppy Drive. Now, documentation for this card is very scarce, so I didn't even know how to use this card, let alone I don't have any discs for it or anything like that, so I didn't even bother to try it out. But since I made those videos on this machine, one of my patrons reached out and they found some technical documentation for this card, which gave me the information I needed to actually use it. So in this video, I'm going to make a floppy disk and I'm going to see if I can get this computer booting into DOS, which is obviously made for the 6800 processor. So without further ado, let's get right to it. Okay, so this is the BFD-68 from Smoke Signal Broadcasting. I notice here a little sticker that says Hank White, and I wonder if that was the owner of this computer at some point. So, as you can see by the floppy connector here, this is a floppy controller for the Southwest 6800, and it's got the SS50 bus connector here. And this is different than the actual floppy controllers that Southwest released themselves, which was only the SS30, which would have been this size connector, that plugs into the slots on the back of the machine. From my understanding, this card was actually released before the floppy controller that was released from Southwest themselves. And one of the reasons for the 50-pin connector is that this has a 512-byte bootstrap ROM, which is this IC right here. And that differs from the floppy controller that was released by Southwest. And the reason why is Southwest just released an updated ROM for the entire system, which contained the disk drive boot code on it. Otherwise, with this card, if it didn't have this ROM chip, you would have to type in some kind of assembly language program into the machine language monitor just to start to boot this thing. Now, the 30-pin slots that are in the back of this computer really can't handle having a ROM chip there, or RAM for that matter, just because of the way the chip select lines work. It really only allows selecting a couple addresses, which is appropriate for I/O chips, which is kind of the design of those slots. Now, once Southwest released their floppy controller and the updated ROM, I think a lot of clone floppy controllers came out that plugged into those 30-pin slots and would work exactly the same way with the same software and everything like that. There are some other differences though between this card and the Southwest one besides the ROM. This actually uses a 6821 I/O controller chip here. I think it's a PIA or a CIA to actually handle all the disk controller I/O. Basically everything going from the computer to the disk controller actually runs through this I/O controller chip here. So that means, unfortunately, the software that was designed for the floppy controller that Southwest released is not going to be compatible with this card just because of the different way that it talks to the floppy controller chip. And yes, they do actually use the same floppy controller chip. I had shown this in one of the earlier videos on this machine, but here's an advertisement for this BFD-68. And to kind of rehash a little bit, it seems that when Southwest sold the disk drive system, it actually came with 1 or 2 or 3 floppy drives and the controller card that went in the machine. And along with the disk drive, Smoke Signal included a DOS disk to actually get this thing booting. And I'm pretty sure that they also released their own software packages as well that were made specifically to work with this disk controller system and this machine. It even mentions down here on the ad here that free patches are provided for BASIC and I guess a co-resident editor assembler to allow load and save capabilities with this floppy drive controller system. So I was looking for information on how to use this card, and besides this advertisement, which we just went over, that's it. I couldn't even figure out where exactly this ROM is in the memory space on the computer because I need to be able to at least start to execute that bootstrap ROM to even start to boot the floppy disk. So that's where one of my patrons stepped in who recently just found this document and sent it over. This is the technical documentation for this card right here. And as you see right here, it has the boot and I/O routines contained on that ROM chip and allows you to do all the read, writes, seeks, all that kind of stuff. Now here's the floppy controller chip. It's the Western Digital FD1771B-01. Very popular chip back in the day. I think the 71 was commonly used and also the 91 was commonly used on a lot of the systems around this time in the late 70s. Incidentally, the date codes and all the chips on here are from 1977 or so. And then here's that section about the ROM here. The ROM located at U17, which is this IC right here, provides 512 times 8, so that's 512 bytes. The ROM addressing is decoded to use unused addresses in the I/O page between 8020 and 83FF. I have to admit, that's pretty smart on their part. Apparently, in the 8000 range on this machine is where all the I/O space is for those 6 or 7 slots that are in the back of the machine. Well, the way the decoding works on this machine actually leaves gaps in between the memory locations that you use to address those cards, to select those cards. So what they did is they actually stuck this ROM into the space between those gaps so that you can have this thing maxed out with 48K like I do here and still be able to address the ROM. I was under some kind of assumption that this ROM was located somewhere else in memory space and wouldn't even work on this computer because the RAM is taking up all of the free space supposedly that I thought would not be available to any of the ROMs. But I thought wrong. They did a pretty cool trick there actually. Scrolling down a little bit, there's a little information here which is actually very useful. It says here that this disk controller uses a standard size mini disk, which is a 5 1/4 inch drive, or disk with 1 index hole. So it means it's soft sectored and not hard sectored. I was worried it was hard sectored, and I actually have some hard sectored disks. Hard sector disks, when you look at the little index hole around the center spindle, actually has, I think, 16 or 12 holes or something like that if you kind of spin it by hand. While a normal floppy disk used on pretty much everything most people are familiar with just has a single index hole, which is used as a pulse to synchronize the disk controller. It's not used all the time, like the C64 or the 1541 drives, and Apple IIs, for instance, don't use the index pulse. But most other designs that use a disk controller chip like this, including the IBM PC and all of those types of things, they do use that index hole. And that's why you can't flip a floppy disk over in a machine that uses it, because it won't see the index pulse and the controller can't synchronize anymore. But on a machine like the Apple II or the Commodore, since it doesn't even use that sensor, you can flip the disk over and there's no problem. One old system that used those hard sector disks was the North Star, which is a pretty common S100 system. If you inadvertently try to format a multiple index hole diskette, the program will report a very large number of bad sectors. And we keep scrolling down here. There's schematics for the entire thing, which is awesome. That's going to mean if this needs repair, it's going to be a lot easier. As we keep scrolling down, here's a whole section on how to boot the system. And this is exactly the information that I was lacking. And here's the key right here. Thus, to load DOS68, use MITbug, which is a trademark Motorola, or in the case of this machine here, we're on SWTPC, which is the updated ROM. And you have to transfer control to location 8020. So that's where the ROM is mapped into that address space. We would just do a J and 8020, and that would start that bootstrap ROM. Okay, so I have the information on how to start to boot this thing. Now I need to get a boot disk because I didn't get the disk drives, which is no problem because it's just a normal 5 1/4 inch drive, but I didn't get any of the boot disks with this system either. And this stuff is really, really hard to come by. Lucky for us, over on archive.org, someone has uploaded the BFD DOS68 version 5.1, which I think is a relatively late version of this DOS as well. There seem to have been many versions released by Smoke Signal over the years. And you notice on this label here, it's CO80 through DFFFF, so it needs to load that RAM into that high memory that I now have on this system using that second RAM card, which I did all those bodge wires on. Now, in that technical manual, it talked about a version of DOS that ran in the 7000 space. I'm positive that that's what was running on this machine when it was actually being used by its owner. And that's because this machine didn't have any RAM in that high address space at all. So this must have been using that other version of DOS that used that lower memory. And unfortunately, that disk doesn't exist. Like, I don't have it, and it doesn't seem like there's an image of that anywhere on the internet. So luckily I have that RAM on here, so I'll be able to use this disk image. And it's not just a picture, by the way. They actually have a CryoFlux image uploaded here. So I'm gonna download this, and we're gonna try to make a floppy disk. Okay, I have a disk drive set up on the bench. We have the CryoFlux right here, and you see the way the lights are flashing. That means that it is working. It's always a little bit fiddly getting this thing working, the drivers and stuff. If you switch USB ports, I have to like manually do some stuff, but I've done it enough times, I'm used to it. So I wanna make sure this thing is working. So one way to do it is you run DTC-C3, which is gonna tell us how fast this drive is running RPM-wise. So it's a little slow. Let's see why that is. I mean, it's probably not a problem, but maybe I should try to adjust that. Is this thing even adjustable? Let's see here. So underneath, there's a potentiometer right there. Let's try adjusting that. So this uses a brushless induction type motor, so it's completely speed controlled by these ICs right here. So I'm surprised it's a little low. Let's see if this changes it. Yep, it does. get that higher a little bit. That's too much. You know, it's funny, I never even thought to try to calibrate this drive. And it's interesting actually, like this pattern right here, I don't know if it shows up in the camera, but with my studio lights, well, the overhead lights, there is a little bit of flicker on them. It's at line frequency. So this outer ring here is for 60 Hertz and the inner one is for 50 Hertz. And now it is rock steady and not even moving. Well, it's moving ever so slightly. And actually, according to the RPM on the screen, it's a little slow. So I'm gonna turn this slightly. There we go. Now it's rock steady and now it's 300.00 RPM. All right, well, that was easy enough to calibrate. I didn't even think to do that. Compared to the older floppy drives, which also had a pot for adjusting the speed, those things didn't have sensors to know how fast they were going, but this drive does. So it's pretty much gonna stay locked on to that RPM unless there's a little bit of drift in that potentiometer and the other electrical components, which there will be, but generally means that the speed is gonna be really stable on this drive. All right, so over here in this window here, this is the download of that Smoke Signal Broadcasting disc. It's the actual flux image and it's really quite big. It's 168 files here. Now it's track 0 and 1. Now the thing is, I'm pretty sure this is gonna be a single-sided floppy disk. I mean, 100% it definitely is. But the person who made the image, they just did both sides anyways. And in fact, I'm noticing here that they did all 80 tracks, which is weird because it would have been a 40-track disc for sure. It's just not high density or anything like that. So it's almost certain that there's gonna be extra tracks in here. So let me open up the HXC floppy utilities here and let's load this flux image in here. We just picked the first file here. This is gonna load the entire image here. It's gonna take a little bit of time because it's a raw image. It has to interpret it all. What I wanna do once this is finished loading is I want to use the disk analyzer or the visualizer to look at where the track data is, because my concern is that whoever made this disk image used a high density disk drive, which is an 80 track drive or 83 tracks in this particular RIP, which means that every other track is gonna be blank, which means we're gonna have to like skip over those. So we'll be able to see that with the disk imager here. But that's the one thing, if you are gonna be preserving disks with a cryoflux, please, if you're doing a double density disk, use a double density drive. It's gonna read it much more reliably, first of all, and then you're not gonna have a problem where you have these potential empty tracks that are blank. Here's the box for the cryoflux, by the way. I've had this for quite a while. I first heard about it on a video from LGR. It is really the device to have if you're gonna do disk preservation. It really is designed for reading disks. It can write them, so I'm gonna be using it to write these flux images back onto a real disk. But it's not great for just writing like arbitrary disk formats. It's really only good for writing its own images back onto disks, or potentially like, I think, Amiga disk images and stuff like that. There are loads of videos online about using this thing, including LGR's first video, so refer to those if you need more information. And there are also alternatives to this device, which I think cost about €100, or at least when I got it. There's the Grease Weasel, which is an open source version of this. It doesn't use the same software, but it does very similar things. I think it's pretty much equivalent when it comes to capability. But I've just had really good luck with this, so I sort of stick with it, and of course I have it. But I have a Grease Weasel as well, and I've played around with that, and it seems just as good. All right, so the image is loaded into here. Let's do track analyzer. All right, so this is what I was talking about in this view right here, where I set to 96 track per inch. I have it set for FM and MFM decoding. So it's gonna try to make sense of the flux data, which is the actual magnetic data on the disk, from an MFM or FM perspective. Now you see these green circles here? That is successfully read tracks. And when I hover over the tracks, you notice over here, it's actually showing some information that's actually stored on them. So that's really cool. Now, you see all these red circles here? That is because this was definitely read on a high density drive. And at the beginning here, there are gonna be issues. Ooh, how am I gonna deal with this problem? Okay, I just enlarged it. So what the green sections are here are the sectors themselves. And you see how there's like a slight amount of warble on them? That's because the drive that either made the disk or potentially the drive that archived it wasn't perfectly stable in the RPM perspective. Over on the left is the first side of the disk, or side 0, and this is side 1. Well, side 1 was never used. It's a single-sided disk, so it's just all red, which means there's no available data on there. And theoretically, every other track that was read is also not valid. Now, problem is they read every track, So there's potentially like these tracks that are read that are sort of an amalgamation of the tracks next to each other, crosstalk, so to speak. And that's because double density drives like this have a wider head because they're only designed for 40 tracks compared to a high density drive, which has 80 tracks. So the head on those 80 track drives is much finer pitch. If you try to read a double density disc, you can end up reading on the half track and you get this crosstalk from the other tracks because the head that wrote it wrote down a wider magnetic track. Also, I'm noticing that the drive that made this image was also running at 360 RPM, which is not the right speed. These discs run at 300 RPM. I think we should be able to handle that problem though, but that is not ideal either. I'm noticing that the innermost track here is track ID 34, which means that this is a 35 track format as well. So it goes from 0 to 34 or track 1 through 35. That was very similar to a lot of the early disc formats on 5¼ inch discs. Later ones used 40 tracks per side, so you got a little bit more capacity out of it. For figuring out the right command to actually write this disc properly, it really helps to kind of read through the command line help, and then I've crafted this right here, which I've pasted in right there with a -F, and we're gonna pick the first track here, like that, and that should do the trick. Let's see what happens. Okay, here we go. Image type raw, image size 2, tracks 40 or 84. Let's see if this actually writes it. Here we go. And what we're gonna do is after I write this, I'm gonna re-image this disc. That's funny, it made that horrible noise. It looks like it jumped up to track 80 for some reason. Okay, and check that out. So it wiped up to 34 tracks, then it tried to go to 80, but then it looks like it skipped every other track writing. So, okay, set track distance. I had it set for 2. I think I will need to change that to 1. Let's see what happens now. My concern here is because the source image is not correct with this disc, that when I write track 0 to 34, it's gonna be missing half the disc. What's gonna happen is basically it's gonna write those blank tracks onto this floppy disk here, which I don't think is going to work. And look, it's not even working. All right, I'm trying to think of what to do here. I think what I'm gonna do is I'm gonna grab a high density drive and I'm gonna re-image this disk on that drive, which should result in a okay disk. Let's try that. Alrighty, we have a TAC 1.2 meg drive, and it runs at 360 RPM, it's 80 tracks. It's exactly the same as the drive that was used for making the image. I'm gonna go erase this disk using a degausser, because the problem is it's been written on a 360K drive with a wider head, which means that this drive, it just doesn't have a good chance of writing to this disk without having leftover data on there, because as the heads erase the old data, it's erasing it with a much thinner head than was originally used for writing. So for best possible results, I mean, this might work fine, is just erase the disk first with a degausser. This is the degausser that I use. It's a Radio Shack high-powered video audio tape eraser. It's great at erasing videotapes, audio cassettes, and floppy disks as well. So you just kind of hold the button and move this around on here. The light comes on. Shouldn't hold it for too long, but that will totally erase your disk. All right, so we can see that this drive has 83 tracks on it, which is exactly like the drive that was used for imaging. And here we go, I'm gonna make the disk image. I removed the parameters that limited the track writing. So it's just gonna write all 83 tracks onto this disk. Although the one limitation that I did make is I told it only to write side 0, so don't even bother with the other side, because we know that's blank anyways. If there's any of my viewers watching who are familiar with CryoFlux and know a way that I could have fixed this problem with command line parameters, so I could have written the image right to this drive, definitely please let me know. All right, notice how it's skipping every other track. I wonder if it doesn't even bother writing those empty tracks that it knows are empty. It's only writing the ones that have the flux information in them. All right, so now this disk is written. I wanna read this in the 360K drive and just make sure that it looks proper and all the data is there. Okay, here's the command I'm gonna use for reading this disk. See if this does the trick. You know, I put this in, -G, side 0, and as you can see, it's reading both sides of the disk, 0 and 1. So, don't know what the deal is with that, but seems like there's maybe a little bit of a bug in this version of the DTC program. It just seems to ignore the side command when you're reading. All right, there it is, it's finished, and at least it did stop at track 35 or 34. Okay, so here's the test disk. Let's load that into the HXC tools. And let's take a look at the track analyzer. And there it is, there's the data. Now notice there's these little like red dots in here. Those could be like read errors or something like that. And I think that might have come from bit rot on the original disk, or the fact that it wasn't a 360K drive that made the image, or whatever. But from what I can tell, this disk image should potentially work. Now, it's just a matter of getting this stuff all hooked up together. Okay, the Southwest 6800 is on the bench. The floppy drive is connected to the disk controller, which I have inserted into the slot right here. The only cable I had that had edge to edge straight through was the one I was using on CryoFlux. Actually has 2 edge connectors on it with no twist, because you don't want to have a twist in the cable going to these older Sugart type drive interfaces. I set the drive to drive select 0. I enabled the termination on the drive. It's the last device on it. And you absolutely need the termination enabled on here. Otherwise, it will definitely not work, because those are pull-up resistors and there won't be signaling from the controller to the drive without it. And I'm going to turn on the computer right now. I just want to make sure the machine even works with this card in here. Okay, we got the $ prompt. If we type R, there it is. There's the register. So we know the machine is working. The drive, it should be on. Let me just make sure it's on. I think the disk should spin. Yeah, the motor is spinning there. We'll leave it out. I'm going to try to jump to that memory location, which I know should start booting. Here we go. That didn't do anything. All right, let's look at 8020. So it's got stuff there. Remember, there's 512 bytes or so in here, right? And it doesn't even seem to be trying to access the disk drive. This may be a termination problem though, or maybe there's a problem with my cabling. Interesting. So the computer is locked up, so it doesn't seem to be trying to boot. Let me reset out of this. And let's just double check that the memory that's there looks the same every time I look at it. So 8020, oops, that's not right, 8020, yep, okay. And I should not be able to write to 8020. Let's just put FF there, okay, good. It puts a question mark, that means that's a ROM. But when we try to jump to 8020, it just sort of freezes up and the drive doesn't start. I would have assumed it would start, although maybe I need to have a disk in here. Jump 8020. Nope, it's not doing anything. I'm just gonna double check that my switch settings are correct. Drive select 0. There's a jumper on here that's labeled TM, which I thought is for termination. I had that selected. I'm just gonna leave that off. Maybe that's a terminator disable, something like that, I don't know. Turn that on, turn on the computer. And now we try to jump to 8020. And nope, nothing again. I went and picked out another 5¼ inch disk drive off the shelf. And there, this has a 150 ohm termination resistor right there. So I know there's not a problem. I'm just gonna set this to drive select 0, because that is absolutely gonna be necessary. All right, this drive is hooked up. Hey, the light blinked. Okay, so that's a good sign. It's quite possible this drive doesn't have the termination enabled and I don't know how to enable it. Also, the drive is spinning right now. That might be something that it just does all the time. Did the light just blink again? J8020. No change. Wait, well, the light certainly blinks, but it's not booting. It is spinning, that's a good sign. Let's turn this off and on again. You see that? The light does show up, says it's doing something. But unfortunately, jumping to the entry vector for that ROM does not work. I just tried to jump to 8023, which is like the warm start vector, and now the light is just solid on. So it does imply it's kind of doing something, although I just hit reset and now the light is still on. So maybe something's going on that floppy card. I'm gonna pull it out. Well, let's reseat all the chips. There's a good amount of crusty, corrosion-y looking stuff like on that IC right there. So this thing may just need a good Deoxit bath. Okay, after reseating all the ICs using Deoxit, it does basically the same thing. When you first turn on the computer, you get a little flash, and then when you execute the bootloader or bootstrap, the drive select light does come on. It's like as if it's trying to boot. But the thing is, this is extremely rudimentary. So if it's not successfully reading this disk, for instance, if there's no error to show up or anything, it's not gonna do that. So the question is this disk not good? Is that why this is not booting? Or is there some other particular reason why it's just not working? Like there's a hardware fault. But you know, what I notice it's not doing is it doesn't seem to even be seeking the heads. I'm gonna go refer to the technical documentation. Maybe there's some setting on the drive that it needs to have to work, that it's not set properly. All right, I'm back. Time has passed and I have made amazing progress. So I have everything hooked up here. I'm gonna turn it on. Notice that the drive LEDs did light up. I'm gonna stick a floppy disk in this drive, which is the drive 0 on the right, and we'll type J8020 to start the boot process. Now, the one thing I didn't realize initially when I was testing this is that there's some kind of a delay in the ROM on the card. It seems like it waits a little while before it even attempts to boot, probably for, make sure the disk drives are stabilized. This is interesting. It's not booting. And I'm telling you that it did just a moment ago while I was doing testing. All right, I'm gonna power that off. I think either this cable I'm using just doesn't always have the best contact on the card. So let's do that. Let's turn it on again. Let's try one more time. I'll talk about what's going on here in a second, but I just want to show a hopeful, successful boot of this system. Okay, lights on. It accessed the disk a little bit and then it shut off. Oh, this is hilarious. Like, this just sort of shows that with these old computers, it doesn't always go according to plan. I'm just gonna check the cables here. I mean, I had this working. Okay, I can definitely tell there's a problem on the cable because if I tweak it one way, the drive select goes on and off. Okay, so I'm gonna turn this off. I'm gonna lift the cable up slightly on the edge connector there. I think the edge connector is a little bit worn, but also this cable that I'm using, I switched to a different cable here that has a facility to have 2 disk drives and there's no twist in the cable. That cable, I think this connector is just, I should replace it. All right, let's try one more time here. 8020. So now, for the 4th time, let's try booting this computer with this flaky cable. Now, this is all part of the problem. Like, when you're testing stuff like this, there are so many things that could be problematic. The disk drive, the floppy disk, the controller, the power supply, the cable. So yeah, it's not even attempting to boot. I moved the cable a little bit. I think it's booting. Okay, there it goes. It actually is booting. So it is definitely this connector on the cable here that is problematic. Now you can hear the drive clicking away, and on the screen there we have the boot sequence. And look, it's actually booted into DOS. Unfreaking believable. Now, unfortunately, I actually got this booting off camera because I was fiddling around for, countless hours trying to figure out what exactly was the problem. So let's just back up a little bit and let me go over all the various steps of trying to figure out what was wrong. So, first off, and I showed that a second ago, when you initiate the boot process with the J8020, there's a little bit of a delay. And reading the technical documentation actually talked about that, and that's normal. I think it has to do with stabilizing the disk drives or something after you turn them on as well. Whatever the reason, anytime you initiate a boot process, there is a few seconds of delay, and it seems like it's even longer when you first turn on the computer. There's a 555 timer on the card that deals with the reset circuit, and I'm not sure if that's holding the reset longer when you first power it up, but regardless, as you saw, before you even get disk activity, other than the first burst when you first turn on the machine, typing J8020, there's just several seconds. Now, when I left off before, it wasn't even seeking the heads. What did I do to fix that? Well, I took the card out again, and even though I'd already done it, and I started reseating the chips, and I actually broke out the oscilloscope and was sort of like poking around, and I just could not find anything wrong at all. And what I was doing for testing is on the disk drive, I think I was using this disk drive here as the 0 driver, the first drive. I would actually physically move the head a little bit while it was powered on, which it doesn't like it when you do that, but if the controller's not doing anything, the drive just sits there. And when you initiate the boot process and it's working, it should seek to track 0, because according to the technical documentation, it's trying to load sector 0 off the disk to initiate the boot process. So one of the times I just put the card back in and I did the boot, and all of a sudden the head moved to track 0. So, well, that was progress. Now keep in mind, I wasn't using this cable, I was using a different cable that doesn't have bad connectors on it, so that there was no, I don't think there was any kind of flaky issue with the cable initially. I switched to this cable because I wanted to try 2 disk drives, and typical Shugart disk interface standard, you don't, or you can't have a flip a twist that is in the cable like PC has. So you can't use a regular PC floppy drive cable. You need to use one that is just straight through all the way, which is what this cable is. I think it came from an old computer of some kind that was pre-PC floppy drive era. So the drive seemed like it was trying to work, but yet when I tried the boot floppy that I had made with CryoFlux, it just sat there and didn't do anything at all. Just the light would spin and that was it. At that point, I did break out the oscilloscope and I was poking around on the floppy controller chip, trying to see if the controller chip was seeing data from the disk drive. And I could actually see that. Now, I don't want to get too technical on the way the floppy controller reads data off the drive, but the data pin comes in over the cable, and then there's a circuit that sort of separates a clock signal, and that goes to the floppy controller chip. So with the oscilloscope, you should see a regular pattern, which is the data that's coming in off the disk drive, and that's what it's decoding. Well, when I put in disks, like other disks, I could see patterns and stuff, so it was reading stuff, but I guess none of it was compatible with the controller. But I didn't really know if there was just a problem on the controller or somewhere else, because it may well have been. What I did is I grabbed a TRS-80 Model 1 floppy disk. Model 1 TRS-80 also uses FM, not MFM like later PCs, but the original FM standard, single density. That's what this controller chip on this card uses. So I stuck in the TRS-80 Model 1 disk. I'll demonstrate that right now. First I gotta take out the disk that works here. So I'll put in this Model 1 disk. We're gonna reset the computer and we will do the boot process 80/20. And hopefully the cable doesn't bite me here, but what happens is it will eventually start to boot once the delay passes, and then it reads the disk, so it's seeked, and then the light shuts off. And that's it, the computer just sits there and it's frozen. But the fact is, with the TRS-80 disk, it did exactly what it did there. It actually seeks the head, reads a little bit, and then shuts off. And I'm figuring what's happening here is it's able to read this disk because it's FM encoding, not MFM like everything else. So that's telling me that the controller's probably working now. Whatever was wrong before is sort of gone for whatever reason, whatever chip was bad or something like that. And that kind of pointed to the fact that the CryoFlux disk image I made wasn't working. Now the problem is I don't have any other floppy disks to try. I don't have any other disk images to try. That's the only known boot disk for this controller in existence on the internet that I could get my hands on at least. So I decided to take a totally different tactic. Well, the original image had like 84 tracks, which of course is too many, and it also had two sides, so side 0 and side 1. So I went ahead and I went into the directory on my computer and I literally deleted all those extra tracks. So I wanted only the even tracks, track 0, track 2, track 4. Those are the ones that had the data on it. All those other tracks were bad tracks that weren't needed anyways. So I physically deleted the files out of here and I deleted all the files for side 2, which would be marked .1.raw. So those are gone. I had to rename all those files so they could be sequential from 0. So it only took a couple minutes. I just manually did it. So 0, 1, 2, 3, etc., etc. So at that point, I was left with a disk image that could be properly written on one of these drives. That still left me with a problem though. The disk image that I had was now a 40-track disk image, single-sided, but it was made on a drive that ran at 360 RPM and not 300 like these. So if you try to write a 360 RPM image onto a 300 RPM disk, it's just not going to be compatible because the way the data is written to the disk will be, I think, too fast or too slow or whatever it is. I already know from experience that's just not going to work. So what I did is I opened up the old HXC floppy emulator software again and I loaded the raw image into it. At this point, when you hit Track Analyzer and we switch over to 48 TPI, there it is. There's the actual disk image and it's looking proper now. It doesn't have those gaps. It doesn't have any of those red marks on it. Notice the entire side 2 is missing. So with what looked like a good image in HXC here, I decided to not rely on CryoFlux to actually write the disk image, but instead to try to use IMD or image disk, which is a really good DOS program I've used a bunch of times to read and write disk images from these older type systems. In the HXC here, you can say export and you can actually pick IMD as the format. There it is. The output is an IMD file. It's around 80 kilobytes in size. And I transferred that new 40-track image, although 360 RPM, over to my PC to write onto a disk. What you see on the screen here is hooked up to my PC that I use for disk imaging. It's actually a machine that's down on the floor. It's not the 5170 here. The reason why I use that machine and not this is this has a high density disk drive in it, and I need or I want to write these disks using a 360K drive. So that is what's in the computer that's down there. In the settings for this program, I configured it for 35 tracks, and incidentally, the cylinders count here starts at 1. So it's not 0 to 34, it's actually 1 to 35. I did one side double step off. Double step is when you're using a high density disk drive and you're trying to read a 360K disk on it. Because it's an 80 track drive, it has to double step to read the tracks properly, because there's only 40 tracks and you're reading it on an 80 track drive. But since I'm using a 360K drive, that is off. But the other key thing that you had to do is down here on these kilobit settings. So 250 kilobit is double density, or single density, which is FM. So that just means if you have a 250 kilobits per second image and you're writing it to the drive, write it at 250 kilobits. So the disk controller is outputting it at that speed. 500 kilobits per second for high density disks, and this is saying that any image that's high density is going to be written with 500 kilobits. But what is this 300 kilobits you see here? Well, if you are reading a double density disk in a high density drive, what happens is because the drive is running at 360 RPM, to read and write a 250 kilobits per second double density image, the controller actually has to run at 300 kilobits per second. Well, remember, the image that we just converted on HXC is actually for a 360 RPM drive, and it's going to show up to IMD as a 300 kilobits per second image. So what I need to do is set this image right here to write a 300 kilobits per second image at 250 kilobits per second. Without this one special setting, the image that it created wasn't going to work. After that, all you have to do is write the disk from file, and it puts it onto a floppy disk, and you stick it in the computer. I did accidentally make one without setting this option, and of course, it resulted in a computer that didn't boot. It would just try to boot and just freeze up like it was doing on all the other disk images. But with this set, it actually created a disk that booted. So I was pretty ecstatic to have this computer booting, and I started playing around with the DOS, and we'll do that in a second, but not all was well. I found that if I did anything on the disk that I had just written on IMD, that it would actually start to corrupt the disk. So I'd start to get disk errors on here, and I noticed if I took the disk that I had just imaged, made some changes to it, like I wrote some stuff on it, and then I put the disk back in IMD and I tried to make a new image of the disk, now that it's been changed, IMD would actually have problems reading the disk, like it would have data errors. So it wasn't like a physical problem, it just had issues reading those sectors because of data issues anywhere I had written the disk. My initial thought was that either the controller or the disk drive or something here was physically wrong that was causing it to write the data incorrectly onto the disk. But to test that, I took a blank disk and I stuck it in the second disk drive, which I had now hooked up, and I used the format command to format that disk. Once it was formatted, I put it back into my IMD computer and I imaged it, and it imaged it perfectly. There were no issues reading that disk. So that implies that the writing circuitry on this thing was actually fine. So I really think it had to do with the fact that that original disk image went through all those transformative steps, all the way from cryoflux to HXC to IMD before it got turned back into a real disk. It must have somehow altered the disk a little bit that caused it to get corrupted by this OS. Being an OS from the 70s, it's probably not super sophisticated when it comes to making sure that there's no issues or with the format or whatever on the disk. So what I did is I formatted the blank disk, I copied the entire contents of the boot disk that when it's made with a fresh copy, it's not corrupted, as long as I don't change anything on it. I copied that onto the new disk, and then there's a command called link, which apparently you have to do to create a bootable disk. So you type link and you point it to like the main DOS file. It's like the command.com kind of thing. And sure enough, when I put that disk in the boot drive, computer booted up perfectly. And then I took that disk and I re-imaged it on IMD. It read it out perfectly. I wrote back another copy onto a different disk, and it was able to boot that disk as well. Fortunately, no one in the future is going to have to go through all that rigmarole, because what I've done is I've downloaded those two cryoflux images off archive.org. There's the DOS boot disk that I was booting this computer on, and there's a Fortran compiler as well designed for this particular version of DOS. And I've done this whole conversion step, copying the disks, imaging it, moving it around, all that stuff. And I've ended up with two IMD images for both of those floppies that is very easy to write All you have to do is get that file and use IMD on a DOS PC and make 2 disks. Those disks that I make with IMD work every single time, they don't get corrupted, they boot the computer without issue, and all the files work on them. I made a little list here of all the things that I encountered working on this, so I remember when I talk about it on camera here to not leave out steps. I did leave out one step of a problem that I noticed. Early on in this video, when I did a dump of the ROM using machine language monitor, I could like see the code there. There was definitely a problem. Well, I couldn't tell at the time, but I could tell after because I still had the scrollback buffer there in PuTTY. If we do M and 8020, which is the start of the ROM, and we look through here, so that's the code right there that we're actually seeing out of this ROM chip right now. When I checked the scrollback buffer, I saw that what it's reading now was different than what it was reading before. And it wasn't just a little bit different, it was very different. So I think there was something wrong with like the decoding or something. It must have been a bad connection because like I said, I didn't actually change any chips on this board whatsoever. I just reseated stuff. And that was also probably causing boot issues early on because obviously the ROM is necessary to bootstrap the entire system. And if that ROM's not reading properly, well, unpredictable things are gonna happen, which I guess it was what it was happening. Anyhow, at the end of that long story, thank you for bearing with me, I now have 3 disks. I have the DOS 5.1 boot disk, and this is specifically for the SWTPC 6800 with this BFD controller. Although I think this works with other Smoke Signal Broadcasting cards, they had like a LFD maybe, and I don't know, a couple different versions of the card and stuff like that. So I think this works with all of the Smoke Signal Broadcasting disk controllers. And then besides the boot disk here, I also have the Fortran compiler as well. This is made for this particular version of DOS. Like one of the issues with this computer is because the memory layout varied from computer to computer. There were a couple versions of the DOS that were released that used different parts of memory. Henceforth, the problem is that because there are different DOS versions, the software you're going to use, like the Fortran compiler, needs to be the right version to talk to the correct memory locations where the disk operating system lives in. Fortran needs to talk to the disk drives and do stuff that the the disk operating system handles, so it needs to be the right version. So on archive.org, there were actually 3 versions of Fortran that were archived, all for different memory locations. Well, the one that I converted and I turned it into an IMD disk image is the one that goes with the version of DOS that is on this machine. Now, I think if you watch these videos on this machine, you realize that this thing is all about hacking and doing your own thing in assembly language or whatever. So all the software comes with instructions on how to modify it if necessary so that you can get software that's designed for some other version of DOS or a DOS that runs in a different location, talking to the correct routines for this version of DOS. Anyhow, the last disk image I made was a blank disk image. And simply I did that because it's no different than just formatting a disk in here and, get a blank disk. Problem is that format process is kind of long and tedious, and it's much quicker for me just to go to IMD on another computer and quickly make up a blank disk. So that's the 3rd image. Now let's boot back into DOS and I'll show you around a little bit. Alrighty, so we'll just reset here, skip back to the prompt. Let's pop in the appropriate disk here. I'm gonna stick the DOS disk into drive A, or drive 0, and I will put the Fortran disk into the 2nd drive. We type in J8020, and then we wait a little while. And there we go, I can tell it's booting, it's seeking. And we get the DOS68 version 5.1c prompt, and then what's running now, or happening now, it's kind of like an auto exec. Because DOS : is actually the prompt, but then there's that set command and there's a get and a star ready. Now to do a directory on a disk, you use the command list. Now every single command on here is actually a program that runs. There's no like built-in commands, at least that I can tell. And checking out the directory here, it actually splits up the directory listing into files and commands. Now commands are just programs that have a $sign after them. That sort of is the execute bit, so to speak. It talks about how many free sectors are on the disk. I think the disk has about 630 sectors. They are 18 sectors per track at 128 bytes each. You'll notice that the file names are 6 characters with a 3-letter or alphanumeric extension with a period. So it's sort of like MS-DOS, but just even less than 8.3. And I've been playing around with this a little bit, and it's actually relatively easy to use. So as I said, the list is the directory command. The set command is like the DOS set command, which we saw running up at the top here. And this configures some stuff about the terminal, I guess, so width and the number of lines and stop and start bit, I guess, and mem max, I assume, is how much memory, or maybe it's the top of memory space, which on this computer is 7 FFF in that lower chunk. I'm not sure why it's 7800 and not 7 FFF, but maybe there's a little bit of stuff at the top of memory with this version of DOS up in the 7000 space as well, or it's just reserving a little bit. Without the manuals for this, I mean, I'm completely guessing at this. Now, I mentioned that this stuff here is like running the auto exec on MS-DOS. There's actually a file here called start.up, and we can use the view command, which is like type on MS-DOS. So view start.up. Now you notice this last line with asterisk ready. I think asterisk is the same as rem on DOS. Yeah, it doesn't actually do anything. So you can just add that to your startup file there just to print messages on screen. This get command is loading sysprint or sysprit.bin off of the 0 drive, which is 0 colon. Like MS-DOS with like A and B colon, this uses drive number, so 0, 1, 2, because it supports up to 3 drives. If I want to look at what's on the Fortran disk in the second drive, I do list, 1, and it's going to load the list command here, and then it's going to actually do the directory listing off the Fortran disk. And there we have the files and the commands that are on the Fortran disk. Now they have the list command on here, so that's like the directory command. They give you the copy command, Fort C, so Fortran compiler, and then the link C, the linker for the Fortran compiler. So after you compile, this is the same as like every compiler in the old days. You compile, then you have to do the link. And that's what gives you like a binary image that you can actually run. Now you notice here I'm doing a directory. The sound of the head seeking, it sounds a little slow, shall I say? And that's because it is. Old Sugart style disk drives had a very slow mechanism for seeking the heads, and the controllers from the software had to seek the head a lot slower or it would miss track skips. Now these drives, of course, are from a PC, they're newer, they can go much faster, and the typical seeking sound you might know on a PC is not how this sounds, and that's just because that delay setting is too high. Increasing that step speed, maybe there's a delay that's set up in the ROM, or maybe it's in hardware, or maybe it's in software like as it loads the OS, I don't know. If you could increase that, it would actually speed up the operation of this machine a lot because a lot of time is wasted seeking. Anyhow, let's keep going here. So view command, like I mentioned, is like the type command on MS-DOS. There's del, so that's delete. Ren, which is rename, those work as normal. Append, I haven't played around with that, but I'm assuming that just lets you append information onto files. There's a backup command. Now, if I run backup, the interesting thing is it doesn't actually work on this machine. Look at complaints here. This version is for Rev 7, 8, 9, and 10 only of the ROM on the controller card. I don't know what version of ROM I have, but it's probably version 1 or something because this is a really old card. There's the copy command, and it works a lot like copy on MS-DOS, at least with this version of DOS68. I was able to easily copy all the files off the boot disk by doing 0 star.star, like for everything, and then I would put 1, and that's all I needed to copy all the files onto here. It took a long time because that seeking is so slow and there's so little memory on this computer that it was only reading in little tiny chunks at a time. But I just went away and did something else. And it has a nice status update even where it shows you what's happening, like copy this to this, that kind of thing. So that's nice. The find command is kind of interesting. So if we do find, and we do list $, what this does is it tells us where the list command loads itself into memory and then where the system transfers execution to actually start the program. Format is formatting a disk, and it's actually relatively easy to use. If we do format, and I think we do /?, it even has some switches on here. So it's adding a little bit of smarts. A lot of these programs, notice how tiny they are, 2 sectors, 4 sectors. This one actually is a bit better in that it has all these commands. So I don't know, 5¼ inch, 8-inch disc, single-sided, double-sided. This controller only supports single-sided discs, so it doesn't even have the signaling for double-sided, even though these are double-sided drives. Fast mode, whatever that does, quiet mode. So anyways, a little bit of help there. There's the get H command, which I don't know what that does. There's the link command. That's, like I mentioned, sort of seems to kind of point to the startup file. And the startup file is this one right here, DOS68 51C, 41 sectors. When I formatted the disk, these 2 files were automatically copied over. I don't know what those do, but whatever those are, those were copied. Maybe that's like the boot sector, but without linking this, it would not boot. There's a repair program, which if I run this, it appears to be, repair, seems to be like a sector editor or a memory editor or something. Like, look at this, we can dump memory with it, or maybe this is actually dumping contents of the disk. I'm not completely sure how this command works. And again, I don't have any documentation, but I'm assuming what this is for is editing the structure of the disk itself. And that's in case it does get corrupted, like while you're writing and the computer crashes or whatever. The structure of the disk is relatively simple on these older OSs, and it was all very thoroughly explained in the manual or technical documentation. So using a command like this, it was possible to go in there and look at the structure and see where there might have been a little bit of corruption and correct it manually. And I know the TRS-80, those DOS versions from that are from the 70s as well, had a very similar thing going on for that exact purpose. All right, so next up there's a save command, and I do know what this is, and I tried to use it and it didn't work. So what save lets you do is save memory. Say you want to save a file called adrian.bin. It's a program that I have in memory right now. Like say I loaded it off a tape or something else, and it's from 000 to 00FF, and the entry point is like 0100. That will save this file onto the disk. Now it's not going to work because this is write protected. And if I saved it as Adrian $, then it could be something I could easily just run like a command. Once you've done save, you're going to use the get command. I thought it was load there. You're going to get something like I'm going to get the list command. I think that loads it into memory, and that's all. That's what it does. And then you do run, and that runs what was just loaded into memory. It's using that entry point to know where to start. So typing run just executes code from the entry point. So that save and get command allow you to basically create your own program in memory or load it from a paper tape or whatever, and then potentially save it onto disk. Now I tried to do this where I loaded a tape from a copy and paste of this S records and then save it. But I didn't quite get it working. It would start running. In fact, it's on the separate disk here. I'm gonna switch to the second disk. This was my blank disk, which actually has a program on it. So we do list, (1). So I have voyage and space. Now if we type one voyage, it's gonna run the program that I basically loaded into memory off tape and then saved to this disk. And there it is, space voyage version 3.2 S or L. But if I type S or L, it just hangs at that point. So it obviously needs a little bit of modification to work properly on DOS. And I think it was that was the name of the game. The documentation you got with the disk operating system was comprehensive enough that if you knew your way around assembly and you had like a disassembler or an editor, you could go fix programs to then work and be compatible with the DOS and even save stuff to disk maybe, or print stuff to the printer, or use other DOS functions that aren't normally available in this system without any operating system loaded at all. All right, there's some more commands on here. Save T, I'm not sure what that does. SDC, I mean, I don't even know what these do. A lot of times it's looking for like a file name to be given with it, which is the disk error 9. I didn't give a file name. I don't know what that command does. Edit C is like a normal editor, and it's a lot like Edlin on MS-DOS. So when you run the edit C command, you get a hash symbol and you hit P, that prints the file. I thought it did. Maybe it was L, no. You know what, I don't even know how to use this thing. Overlay. Anyhow, there are different line numbers, and if you type in like 6 here, right? So there's a asterisk, and I type 6.00 equals Adrian Black. Now I think if we type in 6, you see Adrian Black. And then to save this, you type log, which kind of outputs the changes I made, which was just to that one line, back to that disk. And now if we do view sprint.txt on the second drive here, then my change to the file is right there. So by the way, generate a printer device for use by the P command. This is for a serial printer on 3, and look, it gives you this assembly code right here. Now the fact that this file here, which is on the DOS disk, is in assembly language, does tell you that there is an assembler on here, and it is right here. It was almost the next thing I was going to get to, assembler BC. So that command will assemble the assembly language stuff that's on here. So if you use that text processor editor and you write some assembly code, or you edit some, or do whatever, download some, then you can assemble it and turn that into executables. So can you imagine like a personal computer in the 80s coming with an assembler with the regular DOS disk? But back in the day with these computers, you were expected to have to modify things to get stuff working. That was just the way it was with these machines. There's also a do command, and then the last thing on here is basic, which people are probably wanting me to run for a long time. I can't remember who made this basic here, but it does work. It's the normal basic. I think it says computerware, which I think is TSC. Anyhow, this version of basic is modified for this DOS system and this controller, so you can do, I think, flist, and you can do load and save commands and load basic right onto the disk. So if we do a command 10 print hello there, this is Adrian's digital basement. There's my little program. If you type run, this is the weird thing about BASIC. It sort of pauses there before it starts. And that's the way that this version of BASIC works, even if you're not using DOS. So if we save this, save it to the second drive, flist, (1) maybe. There we go, that actually works. And there it is, Adrian.bas. I think if we type DOS, that exits out. View, Adrian.bas. And there it is, there's the BASIC program. So we go back into BASIC, and of course on here there's nothing loaded right now, so we do load one Adrian.bas, and that will actually load my program list. There it is. Now you have to think about how revolutionary that capability to have a BASIC program load and save so easily from a disk is. If you're dealing with tapes or paper punch before that, this is pretty revolutionary. I loaded that BASIC program, which albeit is a very tiny program, super quickly. Now what I haven't figured out how to do is get files on and off these disks like outside of this computer. So if I want to transfer a program onto this thing, I'm not quite sure how that works. I also don't really know how to adapt tape-based programs to be saved and work with this DOS operating system. Either way though, it's probably all doable. It's just that I'm more a hardware guy and the software stuff like this is a little bit above my pay grade. Anyhow, I think I'm gonna end this video here. I mean, I've done a lot of talking here. My voice is getting a little bit raspy actually, but I wanted to give a little bit of a tour of this 70s operating system running on a computer from 1975. I'm also, of course, gonna put links in the description below to that technical document, which I showed early on, and all the disk images that I've been using for these floppy disks and stuff. So if you wanna read that stuff and check it out for yourself, you can do so. Anyhow, I think finally we're at the end of this video. So if you thought this, look at this old DOS stuff was interesting, a thumbs up would be appreciated. And thanks to my patrons, their names are scrolling up this side of the screen. If you want to become a patron, you can do so at the link in the description below. There's a whole series of videos on this computer, so if you haven't watched any of those, there'll be links down below in the description so you can check those out. Put your comments down below if you haven't already, and there's also a second channel I have with different stuff on there, so check that out if you haven't already seen that. So that's gonna be it. Stay healthy, stay safe, and I will see you next time. Bye.